Assalamu alaikum, welcome back to EE340. In the previous lecture we talked about wave propagation and lossy media. So we noticed that the wave will experience, the electromagnetic wave will experience some sort of attenuation as it propagates in a lossy medium. We did define some parameters that characterize wave propagation in such media. Instead of listing those parameters, we're going to solve problems related to that topic. It's very important that we keep in mind the following things. So the first thing is lossy media conductivity is not zero. The second thing is wave will attenuate. So let's start with the first problem. So all of problems were taken from the textbook. So this problem says a lossy dielectric has an intrinsic impedance of 200 ohms, and this intrinsic impedance is actually complex, so it has a magnitude and phase at a particular frequency. So what we want to do is actually to find, we are given the magnetic field H here, and we want to find the electric field and the attenuation constant alpha. So let's start with the attenuation constant. So we know the attenuation constant is given by the following formula. And the phase constant beta is given by a similar formula, but instead of -1 we're going to have +1. So if we take the ratio of alpha divided by beta, we will get an equation that's not a function of frequency. Let me call this parameter x. So I'm not giving myself enough space, so let me write it here. So if we take the ratio and set similarly, I can copy numerator here paste it over there, but -1 is replaced with +1. So this ratio is not function of frequency, so the fact that we don't know the frequency is not relevant. So now we don't know we don't know epsilon naught, we don't know mu naught, and we can't actually factor them out here. So the ratio will be so the only missing part here is sigma divided by omega epsilon, and this one is the loss tangent, and we know from the previous class that this one is actually twice the angle of the intrinsic impedance. So we know the angle of the intrinsic impedance, which is 30 degrees or pi over 6. Twice of that is pi over 3. And in this case, tangent of pi over 3 is equal to square root of 3. So we can substitute that back, and we will end up with 2 minus 1 divided by 2 plus 1 to the power 1/2. Therefore, alpha is so if you solve for this expression, you will end up with square root of 3. So 87 parts per meter. So now we know that we know alpha, and we are given the intrinsic impedance of the medium, so its magnitude will be used to scale the magnitude of the magnetic field here. And its phase will be added to the phase of the electric field. So the next step is to determine the direction of the electric field. So from this equation, from this expression, we know that AH is along the positive AY. The wave is propagating along the positive AX here. Therefore, using the following equation, which we showed in the previous class, AA should be negative AC. So now we have all pieces to to write the final form of the electric field. So the electric field will be the following. So 200 times 10, which means 2000, exponential of negative 0.287 cosine omega t. We're not given the frequency, so we can keep the expression as it is, minus 1/2 x minus pi over 6, and the unit is volt per meter. And the direction is along the negative z direction. So now let's solve another problem. We're given a material, alumina, and it's used for making printed circuit boards. So at that specific frequency, at 15 gigahertz, we have specific epsilon naught, or specific permittivity, and specific permeability. We are also given the loss tangent. We are asked to find the penetration depth and the total attenuation of a thickness of 5 millimeters. So the penetration depth is defined if this is the expression for the electric field. This is the magnitude, this is the phase, this is the magnitude, and it's scaled. This is the magnitude, and the magnitude, this is the attenuation constant, alpha. So we want to find the point at which the magnitude of the electric field will be almost 36% of its original magnitude. So if we solve for that, and that's called the penetration depth, delta. So delta will be 1 over alpha. So we want to first find the attenuation constant, and from that we can actually find the penetration depth. So we know the expression for the attenuation constant. We can easily substitute. And if we substitute, we will end up with 0.146 nipples per meter. So delta will be 1 over alpha, which is 6.85 meters. So this formula, or this expression, or this value says that if the wave propagates 6.8 meters inside the material, then it's going to lose 63% of its original value, of its original magnitude. So the second part is we want to calculate the attenuation over a thickness of 5 millimeters. So we know the attenuation constant, and this is we found here, and the distance is 5 millimeters. So the attenuation is 0.73 times 10 to the power -3 nibbles. So let's take another example. We have an non-magnetic medium with the following magnetic field, and we want to find the electric field. So in general, the electric field is expressed in the following form. And the unit vector, the wave is propagating along the positive x direction, and the H field is along the positive y direction, which means that the electric field should be along the negative z direction. And the unit is volts per meter. So in order to find the electric field, we need to find the intrinsic impedance of the medium. So the fact that the medium is non-magnetic implies that mu is equal to mu naught. However, epsilon is not equal to epsilon naught. So let's find eta. So remember, in general, eta is given by the following formula from the previous class. So if I multiply both sides, if I multiply the numerator and the denominator by j omega mu, I will end up with the following expression. So from the previous class, this is exactly gamma squared. Therefore, eta can be expressed as j omega mu divided by gamma. So gamma, remember, is a complex quantity and it's defined as alpha plus j beta. So from the magnetic field expression, we know alpha, which is 100. We know beta, which is 200. And we can directly substitute the values. Therefore, eta is 35.31, angle is 26.57 degrees, and it's an impedance, so the unit is ohms. So now we can substitute the values. So the electric field is now Now let's take the last example. So in a certain medium we have mu is equal to mu naught, and epsilon is equal to 4 times epsilon naught. We are given the magnetic field, and we are asked to find the first thing is the period, then the wavelength, then the electric field, and finally the phase difference between the electric field and magnetic field. Remember, if there is no loss, then the electric field and magnetic field will be in phase. Since the medium is lossy, the electric field and magnetic field will not be in phase. There must be a phase difference between them. So let's start with the first one. Let's find the period. So T is 1 over F, and it's going to be 2 pi divided by omega, 2 pi divided by pi times 10 to the power 8 . So the period is 20 nanoseconds. So the second one is asking us to find lambda, and there are 2 ways to do that. So the first one is, we know alpha, so we can find beta from alpha. And we use the fact that beta is 2 pi divided by lambda to find lambda. And that's what we're going to use. So let's start by finding beta. So remember, we have, let me copy these formulas. So if I square alpha, I will get rid of the big square here. And that's going to leave me with mu epsilon divided by 2 times 1 plus can do the same with beta, and they will end up with something similar, but instead of -1 it's going to be a +1. So now let me do the following. Let me subtract alpha square from beta square. In this case, I will end up with the following expression. Omega square, so that the subtraction is omega square times mu times epsilon. Therefore, beta becomes so I will always take the positive root, since the negative root is valid if we have metamaterial. Therefore, if I substitute all the values, I have omega equals to pi times 10 to the power 8. I have alpha equals to 0.1. I have mu is equal to mu naught. I have epsilon is equal to 4 times epsilon naught. I will end up with therefore I can find lambda from the following formula, which is d meters. Remember, this is the wavelength inside the medium, inside the dielectric. It's not the free space wavelength. So part C is asking us to find the electric field. So in order to find the electric field, we need actually to find the intrinsic impedance. So the only missing piece here is actually the loss tangent, and we'll see why. So let me start by finding the loss tangent. So instead of subtracting alpha from beta, let me add them up. In this case, I'm going to end up with omega square mu epsilon times 1 plus so if I call this one x and substitute all the values, I will end up with x equals to 1.0041, which means that x squared equals to 1 plus and that gives me, so this one is the loss tangent. So the loss tangent is 0.089, and again it's unit list. So now let me find the magnitude of the intrinsic impedance. So the magnitude of the intrinsic impedance is given by the following formula. So this term is actually x from the previous analysis. This one is a very interesting term. So if I expand it, it's going to be 1/2 times square root of mu naught divided by epsilon naught, and this term is the intrinsic impedance of the free space, so it's 377 ohms. Therefore the magnitude of eta is divided by which is 188.1 ohms. The angle we can directly substitute the formula here. One half so this one is the loss tangent, therefore the angle is 2.6 degrees. So now we have every piece to write the electric field. Except the direction, which we'll determine soon. So Peter was 2.098, and the wave is propagating along the y direction. So the magnetic field is along the x direction. The wave is propagating along the positive y direction, which means the electric field must be along the positive z direction. Therefore, we have here a positive z, and the unit is kilovolts per meter. So the last part is asking us to find the phase between the electric and magnetic field, which is exactly the phase of the intrinsic impedance here. So the phase difference so let me not confuse you with this formula. Which is 2.6 degrees. So thank you very much, and the next lecture we'll talk about, the next video will talk about simple cases. We'll talk about propagation if the medium is free space, or if the medium is lossless, or if the medium